Let's solve problem 1 from homework 8, which you see in this QR code as a link to it. Okay, in the depicted circuit, initially the capacitors are uncharged, so Q equals 0 on every capacitor. And the switch S at the top here is in position 1, which I've drawn in magenta, so that the battery is not connected to the rest of the circuit. At time t equals 0, the switch is rotated counterclockwise, so the bottom moves to the right, thereby connecting, putting the switch in position 2 so that the battery then begins to charge the capacitors. So we want to know an instant right after that switch is moved from position 1 to position 2, what is the current through resistor R1, which I've drawn as this purple downward arrow I1. Okay, so I moved the switch over to position 2, so current is flowing out of this top side of the battery, across the top, down through the capacitors and resistors, back through R2 up into the negative terminal of the battery. So because we started out with the capacitors uncharged, and we have resistance limiting the rate at which current can flow, so it takes some time for charge to accumulate on each capacitor. So since Q equals 0 on this capacitor and on the other capacitor, before t equals 0, they started out discharged. The very instant after we move the switch, we still have Q equals 0 on each of these two capacitors for that instant until they have accumulated non-negligible charge. So in that case, the voltage drop across each capacitor is 0, since the defining equation for a capacitor is Q equals CV, where V is the voltage between the two plates of the capacitor. So the voltage between the two plates of capacitor 1 is just Q1 divided by capacitance 1. So that would mean, for instance, if I call this point A and I call this point B, this voltage that I'm referring to here is VA minus VB, which we more conventionally write as VAB. And then if the current is flowing as indicated, then this plate becomes more positive. That's going to be plus Q1. And this plate becomes more negative. That's going to be minus Q1. So immediately after t equals 0, when we've just flipped the switch, we still have Q1 equals 0, we still have Q2 equals 0, which means the voltage across capacitor 1 is still 0, and the voltage across capacitor 2 is still 0. So then we could write the loop rule as the battery EMF minus, so then here's the voltage across that first capacitor, which is 0, and then minus I1 R1, and then minus the voltage across that second capacitor, which is 0, and then minus I1 R2, so we've gone all the way around the loop, so that equals 0. So we went around the loop from the top of the battery down through this capacitor, which had, basically is like a wire at this instant when it's completely discharged, through R1 downward, through capacitor 2, which also is like a wire at this instant when it's fully discharged, and then across and back up through R2 to the negative terminal of the battery. So then we can solve immediately for the current through R1. That gives us that I1 is just the battery voltage divided by R1 plus R2, which equals 90 volts divided by 100 ohms. So that is 0.900 amps to 3 significant figures. The next part of the question asks, what is the potential difference across resistor R1 at time t equals 1500 microseconds? Now, you know the potential difference across R1 is just going to be the current through R1 times the resistance R1. So this question is essentially asking you what's the current through R1 at time 1500 microseconds. And then we have to convert that to a potential difference across R1 by multiplying by the value of R1. So whether charging or discharging a capacitor, the current that flows starts out at its maximum value and then decreases exponentially. So the current starts out at its maximum value, which we just computed. It was the battery voltage divided by the sum of R1 and R2. That was the current through R1 at time 0, immediately after we moved the switch from position 1 to position 2, and then it's going to decrease with this decaying exponential shape, whose time constant is going to be RC, but because we have multiple resistors, multiple capacitors, it's going to be the equivalent resistance times the equivalent capacitance. In this case, R1 and R2 are in series, so the equivalent resistance will be R1 plus R2, and C1 and C2 are in series, so the equivalent capacitance will be the series combination of those two capacitors. So let's work that out. So we have we have this result from a moment ago that the initial current was the battery EMF divided by R1 plus R2, and that was 0.900 amps. And then the time constant is the equivalent resistance times the equivalent capacitance. The equivalent resistance is just R1 plus R2, which is 100 ohms. And then the equivalent capacitance is 1 over C1 plus 1 over C2, the reciprocal of that, which, if there are only two capacitors, a quicker way to write that is C1, C2 over C1 plus C2. Just be careful not to try to do this with 3 or more capacitors. You'll get the wrong units. So 30 times 10 is 300, divided by 40 is 7.5 microfarads. So then the product of these two numbers is 750 microseconds. You have to be careful. Micro is 10 to the minus 6. So ohms times farads is seconds. So ohms times microfarads is microseconds. So be careful. A farad is a really big number for capacitance. So capacitors are more commonly measured in microfarads. So remember that micro is 10 to the minus 6. So now we know that I1 at t equals 1500 microseconds must equal I0 e to the minus 1500 microseconds divided by 750 microseconds. So that is 0.900 amps times e to the minus 2, which is 0.1218 amps. I like to keep an extra digit for intermediate results. So then the voltage across R1 which you see this is like the way I labeled my circuit, that means like VBC. That's like VB minus VC, and you know if the current's flowing that way, then point B should be a higher potential than point C. This is I1 R1, so it's this number times 40 ohms, which is 4.87 volts. Okay, so that was part B. Now in these RC circuit problems, the trickiest part is when you're asked about some intermediate time where you have to use the exponential function. But there are almost always questions about what happens immediately after you close the switch and what happens a very long time after you've closed or opened a switch. So immediately after you've closed or opened a switch, the charge on the capacitor doesn't change instantly. Because of the presence of the resistors, it takes some finite time for the charge on the capacitors to change. So in these RC circuit problems, the charge on the capacitors immediately after you flip the switch, that very instant after you flip the switch, is the same as the charge on the capacitors that instant before you flip the switch. So that's the key to working out things like what was the current right after we flipped the switch. We said, aha, there's zero charge in these capacitors, therefore there's zero voltage drop across these capacitors. Now, the other time that you're often asked about is a very long time after the switch is opened or closed. So after a very long time, the current becomes zero through the capacitor, which means that's equivalent to the statement that the charge on the capacitor becomes constant, because in this case, this current equals dq dt. I mean, it's dq1 dt, and it's also equal to dq2 dt, because this current is adding positive charge to q1. It's moving positive charge away from this bottom plate of q1. It's adding positive charge to this top plate of Q2. It's moving positive charge off of this bottom plate of Q2. So it's making, and Q1 is the label that we give to the positive charge here and also the negative charge here. And Q2 is the label we give to the positive charge here and the negative charge here. So this current flowing is making Q1 bigger. It's making Q2 bigger. So this current is the rate of change of Q1. It's also the rate of change of Q2 with time. After a very long time, this current, which is charging these capacitors in this case, becomes zero. The charge on the capacitors becomes constant. So then the trick to solving this what happens after a very long time question is to notice that then I1 is zero after a very long time. So then we could write the loop rule and say, well, the battery EMF minus, so the voltage across capacitor 1 is Q1 divided by C1. And then you see we have I1 R1, but I1 is 0. And then we have minus the voltage across capacitor 2. And then we have I1R2, but that's 0 because I1 is 0. So that is all 0. And now these two capacitors started out with Q equals 0, and it's the same current charging them both. That's kind of equivalent to the statement that these two capacitors are in series. So you know they have the same charge. So two capacitors in series have the same charge. As soon as I said that, I tried to think of possible exceptions. You could imagine some really weird scenario where at time 0 you have a non-zero charge on this capacitor and you have 0 charge on this capacitor. And then I think it would take some time for things to develop after that. But in this case, we know both capacitors started with zero charge at time 0, and then the change in charge on each capacitor is the same because it's the same current flowing through both capacitors. So we know Q1 equals Q2 at this later time. So then we have the battery voltage minus Q over C1 minus Q over C2 equals 0. And this is the same statement as basically this charge is the charge that would be stored on the equivalent series capacitance. You see, so this is the battery voltage is Q times 1 over C1 plus 1 over C2. So that's like Q is the battery voltage times C equivalent, where C equivalent is 1 over C1 plus 1 over C2, the reciprocal of that. So we basically just, with the loop rule here, derived the equation for combining two resistors in series. So the charge on each one of these two capacitors is going to be this battery voltage, 90 volts, times the equivalent capacitance, which we worked out before was 7.5 microfarads, and that is 675 microcoulombs. And then the question actually asked, what's the charge on C1? That's the same as the charge on C2. So so after a very long time, we have Q1, the charge on C1 is 675 microcoulombs. Okay, so that was part C. But if you'd asked about the charge on capacitor 2, it would have been the same answer in this case, because these two capacitors are in series. So a quicker way to get that same result is after a very long time, you know that the current is 0. So the resistors aren't doing anything if the current is 0. There's no voltage drop across the resistor. So what this circuit looks like after a very long time is that we have the battery, and then there's no voltage drop across the resistor. So we can kind of, for the moment, draw the circuit without them. And we have these two capacitors in series with each other. So we have the battery voltage, and again, it's the full battery voltage because this current is 0, so there's no IR drop for the resistors. And then here's this capacitor plus Q minus Q, capacitor 1, capacitor 2 plus Q minus Q. So this value of Q in this steady state when the current has become 0 is just the equivalent capacitance, the series capacitance, times the battery voltage. And that series capacitance is given by either one of these two expressions. 1 over C1 plus 1 over C2, the reciprocal of, or C1 C2 over C1 plus C2. So we worked that out before to be 7.5 microfarads. Okay, and that's multiplied by the full battery voltage. We've seen other examples of problems where the voltage across the capacitors in the steady state is actually smaller than the full battery voltage because there was still some other IR drop somewhere. We'll see one of those later. Okay, so after the switch has been in position 2 for a very long time, we worked out that Q1 equals Q2 equals 675 microcoulombs. Now we're going to move the switch back to position 1, and we're going to ask what subsequently happens. So we move this switch back to position 1. There's no longer a battery, but we start out with charge on these two capacitors, and then what's going to happen? And I think you can see what's going to happen is the current is not going to flow this way that we've drawn. The current is going to flow the other way, because you have plus charge stored here. So we're going to get current flowing like this. I'll call that I. And it's going to discharge the capacitors. And it's going to have this exponential shape. So it'll start out at some maximum value and it will decrease exponentially. So we have to ask two questions. What is the initial current and what is the time constant? And beware, the time constant changed because this resistor R2 is no longer in the circuit. So let's first figure out what is the initial current. So we know the voltage drop across each capacitor, and so we can then use the loop rule to figure out that current. So let's do that. See, so now like this separated charge on the capacitor, like essentially it kind of acts like a battery. So we can start at the bottom and we can say Q2 over C2. That's that voltage, because you know a capacitor has Q equals CV, so the voltage across the capacitor is Q over C. The one I memorize is Q equals CV. So whenever I want to write this, I usually have to write this and then rearrange. So there's Q2 over C2. And you have to make sure you think about that you've got the signs right, but this makes sense. So this is a positive voltage. And then we're going this way. So then this is minus IR1, because I'm going, you see this current, a positive current here is going to reduce Q2. That makes sense. And then a positive current here is also going to reduce Q1 because it's going to make the plus plate less positive and it's going to make this minus plate less negative. So then this is plus Q1 over C1, and then we're back where we started, so that equals 0. So this, and actually this statement is true the whole time, it's just that Q is decreasing, so the current will be smaller than its initial value because Q is getting smaller and smaller, because you know that I is minus the rate of change of Q. I, in this case, I equals minus dq dt. Also, this is the same Q. So we have Q over C2 plus Q over C1 equals IR1. That is actually the same equation as Q over C equivalent. The same C equivalent equals IR1. I'm going to call this I, well, this is fine. This is still true. I was going to put a 0 here. I don't think I need to. So then I can say that I equals Q over R1C equivalent. So in particular, I know that here's my 0. The current at time 0 is going to be 675 microcoulombs divided by R1, which is 40 ohms. And then this equivalent capacitance is still 7.5 microfarads. Both capacitors are still connected. This is an omega for ohms. Okay, so that's the initial current, so we can evaluate this constant. And then we want to know what's happening 900 microseconds later. In particular, we want to know I. Okay, so we want to know I at t equals 9. We reset our watch when we flip the switch again. So at t equals 900 microseconds, we want to know what's that current through R1, and of course actually now it's flowing up instead of down. So that's this I0 value we haven't evaluated yet, and then times e to the minus 900 microseconds divided by, this is e to the minus t, yeah, I mean, here. This is e to the minus t over tau. And, okay, we should work out what this RRC time constant is now. Tau is R, so it's only R1 now because R2 is no longer in our circuit, and then times C equivalent. So this is 40 ohms times 7.5 microfarads. That's like 4 times 75, it must be 300. So that's 300 microseconds. 7.5 times 10 is 75, times 2 is 150, times 2 again is 300 microseconds. So, and then this is 675 microcoulombs divided by 300 microseconds. Divide by 3, that's 200. Divide this is 225. This must be 2.25 amps. It's actually safer to use a calculator, but I think that's right because, yeah, that's the answer I got last time too. Okay, so it seems like this is 2.25 amps. So that we figured out by saying what's the current when the capacitors had the charge value from right after we flipped the switch, which is the same as right before we flipped the switch. And then we have e to the minus, so you see this is 900 microseconds, which is 3 RC constants, so that must be e to the minus 3. So then 2.25 amps times e to the minus 3. I like to use, too bad you can't use Python on your exams. 2.25 times e to the minus 3 is 0.112 amps. So I believe that is the answer for part D. That's what I got before also. And then it flows downward. The problem doesn't ask you that, but it flows downward through R1. No, oh gosh, it flows upward through R. It flows upward through R1. It flows upward through R1. So it flows upward through R1. That's funny. In my solution, I wrote downward. I guess I have to fix that. It flows upward. It flows the opposite way, right? It flows in the way that it discharges the capacitors. So it's flowing upward through R1. Okay.